This is GS Programming 2, GST 8010, Module 10, Lecture 1 of 1, on GS formats and the cloud. I'm your instructor, Robert Hewlett, and you can contact me via the email address below. The general learning outcome is to master, know, and understand all content and concepts discussed in the lab, lecture, and the assigned readings. Specific learning outcomes, although not an absolute list, describe the use of a BOM, discuss common geospatial binary formats, distinguish between geospatial binary formats, discuss the shapefile technical specification, discuss the OGC well-known binary technical specification, discuss the geopackages technical specification, discuss the runtime geodatabase format, distinguish between common magic numbers, distinguish between common geospatial text formats, that being OGC well-known text, GeoJSON, ESRI-JSON. Discuss the ST geometry format. Discuss protocol buffer format, or PBF. Compare and contrast Parquet and flat GeoBuff. So, BOM or no BOM? So what does BOM stand for? Byte Order Marker. So sometimes at the beginning of the file or quickly thereafter. Sometimes the very first thing in a file is something called a magic number, which we'll get to later. But either right at the beginning or right after the magic number, there's another number burned into the file that tells you the byte order marker. All right, so what are the order of the bytes? And the two orders are high, which is also called big endian, or low, which is also called little endian in that. And so if we were to take a look at money, here's a money amount, okay? And then the question becomes, if you could only have one of the ones, which one of the ones would you want? And so it's not a trick question, you just have to think about it in that. So there's an order to how money is done, right? And what we call the most significant bit. And so one of those ones that we see above has a much greater effect on the amount than the other one, right? And so which of the ones in this amount is the most important, has the greatest effect on what the number actually is in that? And so here with money, there's a natural order, let's say, from left to right that people understand, right? And so the ones in that amount are not equivalent. They mean something completely different in terms of largeness of the number. And so there is sort of a accepted way of running money and determining money and how we order it. And this is what byte order is about. High big versus low little. So would you want the one on the left or the one on the right if you can only choose one of them? I'll leave your choice up to you, right? So this affects multi-byte data types. Things like int32 that uses 4 bytes, or int64 that uses 8 bytes, or a double that uses 8 bytes in that. And so there's more types than this, but a lot of these types are affected by this ordering. So when we just had 1 byte, well, there was just 1 byte. Doesn't matter who is on the left or the right because there's just 1. But when we have multi-byte data types and there's 8 bytes in the sequence, order matters. Okay, and so where it really comes into play is when something gets written to disk. How did you write the order down? Did you go byte 8, 7, 6, 5, 4, 3, 2, 1? Or did you write it down 1, 2, 3, 4, 5, 6, 7, right? And so it depends like how it gets written out to disk. And this one will be high byte order, okay? Most significant bit on the left, and low little byte order, most significant byte on the right. Flip a coin. If you're going to build an OS, right? Actually, it's if you're going to build a CPU chip, in that's where it happens. And so the biggest, I guess, break would be Intel, low little, versus a lot of RISC chips, which are high big, right? So back in the day, a lot of these RISC chips were like Unix style chips, HP Unix, DEC Alpha, and that. But a recent newcomer on the block, and not so new, has been ARM, which is also RISC in that. Very so if we go with the most popular chips out there, we might, it goes back and forth depending what is harnessing our attention in that. And so this affects binary data typically, and definitely affects spatial binary data. Would affect almost any binary file, unless the people who designed the file format designed it in a way that it didn't matter, or in the specification specified what the byte order is. And all you have to do is read the technical spec, and then you know what's going on in that. And so it really is a flip of the coin down here on the CPU. Which way did they do it? 8, 7, 6, 5, 4, 3, 2, 1, right? So there's lots of things where we count down when you launch a spaceship, right? There's a countdown. 10, 9, 8, New Year's, right? We count down. And then there's sometimes when we count up. And so it depends. And so some systems went one way and some systems went the other. But as long as we are consistent, some languages like Java always write high, always read high. So if you tell Java to write something out, it'll always write it out in high byte order. And when it reads it in, it'll always read it in high byte order so it doesn't make a mistake. But when someone else designs a spec, it's really up to them, hopefully, to decide one way or the other. Or if they mix it, they tell you when, hey, this part of the file's low, this part of the file's high. So let's talk about shapefiles in that. So there's a link if you want to go pull the PDF to get all the gory details in that. But a shapefile header starts out with 100 bytes. So there's some magic numbers in there. There's some, like we could say metadata, but that gives you a little bit of an inkling about what the data is in this shapefile data set. In that, if you ever encounter a shapefile, the .shp file that's 100 bytes only, all you have in there is the header and you have no data in that. So they don't use all 100 bytes, but they reserve the first 100 bytes for, overview information that describes the whole data set in that. And we're going to get into what that information is. And then there's a record header. So every feature shape that's stored in a shapefile has a little bit of a header. Usually this is how big I am or something like that in that. And then a chunk of data. Now this data is variable length. It's not a fixed width format. So if we need a lot of vertices to describe a polygon, it'll get wider. If you only need a few vertices to describe a line, it'll be shorter in that. Points are pretty consistent because they usually everyone has an X and Y value. And so their record contents are usually the same size through the file. But when you get into lines and polygons, how many vertices they're going to have, we don't know. Okay, in that. And so it's called a variable length record. Some are shorter, some are longer. But the header usually tells you, basically, gives you enough information to figure out, well, how big is this thing? So that you know where the next record starts in that. So the idea is that it's not fixed width, that record content size is fluctuating. So your features are kind of like shrink wrapped, so you don't have a lot of unused space in the file in that. But the first 100 bytes reserved for almost, we could call it like metadata a little bit, but it describes, hey, what is in this shapefile? a little bit about maybe some uh, spoiler alerts on how it's formatted and that. Okay, so this is how the shapefile header is broken down, the first 100 bytes. What you might notice is that they specify the byte order. That's why it's a platform independent data storage format, because they actually did specify the order. If we look at this, it's like big, 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 all of a sudden in the little, little, little. So instead of going like all big or all little, the file is mixed in that. Would have loved to have been a fly on the wall in that meeting where they hammered that out and that sort of thing. So the very first byte in that, I'm not sure of this, yes, there. So there, 9994, magic number. Hey, I'm a shapefile in that. They have some unused space, 000. I'll get my laser pointer on here. So we have some unused space, and this would be for like trying to future-proof the format. We're going to reserve a little space in the header just in case, we come up with something we haven't thought of yet in that. And then the version of the shapefile, it's been at version 1 or 1000 forever. So the person who wrote this nailed it out of the gate and didn't have to do any updates and that sort of thing. In that file, I'm not sure if I highlight this one, but file length, you can check this. Hey, my SHP file should be this big, and you can go check to see, hey, is it that big? Notice this designation on the 16-bit words. We'll get into that. But a big thing around byte 32 is the shape type. So in this header, it'll say, hey, I'm a point. Hey, I'm a polygon. Hey, I'm a polyline. Hey, I'm multipoint. So it's like a geometry type. So what kind of geometry is stored in this file? If you've ever opened up shapefiles in Pro and the catalog, you'll notice they have a slightly different icon than the file geodatabase or the feature class. And if it detects, hey, these are points, you get a little point icon. If it detects it's lines, you get lines. If you detect polygon, you get a polygon icon. How do they do that? Well, they come in here into the header, and byte 32 tells them, hey, I'm a point, line, or polygon. They assign a different icon to it based on that. All that's happening in the background, at C++ speed usually, but that is what's happening. They go snoop the header. Hey, what do we got? Hey, it's a shapefile. Hey, byte 32 says it's point, line, or polygon, and that. Another thing is there is a bounding box that is supposed to describe the extent of the whole data set. So all of the points, all of the lines, all the polygons, all the multi-points within the shapefile data set. This is like the minimum bounding rectangle that describes them. If we look closely at across, we'll see that it's x min, y min, x max, y max, and we see z min, z max. So it's a three-dimensional. Shapefiles are actually three-dimensional. They pack a lot of 2D data, just doesn't get used. No, 2D data does. They have a lot of shapefiles just have two-dimensional data in there, but it is spec to have 3D data, and it even has measures, so we could argue that it's a four-dimensional spatial format. So it's got X, Y, Z's plus measures in that. And again, this is just the first 100 bytes. It just basically describes the file that you're looking at. Hey, I'm a shapefile. Hey, I'm a point shapefile. And that, hey, the extent of this data set is this minimum bounding rectangle in that. Now that shapefile geometry, the value you'll see in there is 0 for null shape. We'll see that point is 1, okay, and that, and we'll see other ones in here, polyline. And this is a word that Esri uses. If we were in the OGC, the concept of a line or arc over there is called the line string. So in the end, these names matter, but this is classic nomenclature that you see on the ArcGIS Esri side in their libraries like the Maps SDK. They use point, polyline, polygon, right? So polyline shows up as well in that. And so if you see a 5 there, you know you're dealing with a polygon. And if you see different numbers, you know you have a different type of geometry. And it's important because when you're reading through the file, you can't get out of sequence or out of step with it in that. And so those first 3 we just went through, point, line, polygon, right? I don't know if it's implied, but that means it's two-dimensional. It means that when you go get coordinates, there will only be an x and y value there, right? These other ones, if you saw point z, then the person reading through the file has to know to read not 2 doubles out for x and y, but 3 doubles out for x, y, z. If they don't do that on every coordinate, they'll get out of sync with the file and they'll get bad numbers back. Now, one thing you might have noticed is that there's gaps in the sequence. Okay, so is it always odd? No, you got some even numbers in here. But what you sometimes do with these sequences is you on purpose you put gaps in case, hey, we come up with some other type of geometry in between point and polyline, right? It's almost like reserving space for the future and that. So most encoding systems that encode geometry and binary have to have some type of system like this to basically, code the values, right? Because all binary data, and we can make lots of arguments that text data is just binary data with a convention that says, read 1 byte at a time and map it to a character on the keyboard. But when you look at the file, when the computer looks at the file, it's all ones and zeros. Binary, it's definitely ones and zeros and that sort of thing. And so it's just a bunch of numbers in there. And by the computer looking at the numbers and having maybe some lookup table somewhere else, it goes, hey, I'm looking at a point. Hey, I'm looking at a polygon. Hey, I'm looking at a polygon Z down over here, right? Which would mean, hey, I have to remember when I'm going through the coordinates to go X, Y, Z, not just X, Y. Otherwise, I'll get out of sync with the file in that. So we talked about the shapefile record header in that. And so the very first one will be record number. It's like object ID or fed feature ID. Hey, I'm record 1, record 2, record 3, record 4, and that. And notice that they're all big. Okay, and then the second byte. So we kind of read 2 integers out. The first one tells us, hey, I'm my object ID, I'm 1, 2, 3, 4. But the next chunky information, content length, tells us how big that variable length record is. Remember, they can be different sizes. And so that size is stored in here. It's interesting, the record contents are measured in 16-bit words. So you have to take the number, the computer has to, take the number it finds in here, has to remember that it's in big byte order. It also has to remember times it by 2 to get the actual size in bytes in that. Okay, so this content length needs to be multiplied by 2 typically, which may sound weird, but that is the spec in that. And so you take that number, you times it by 2, and you know how many bytes you have to skip ahead in the file to get to the next feature in that. Okay. Now, what we'll go over here is once you get past the header is the same for all features. What's your number? How big are you? What's your number? How big are you? What's your number? How big are you? And then we get into, well, if it's a point, and this would be a 2D point, it'll say, hey, you'll read an integer in, hey, I'm a point, just confirming it. It is written up in the header, but each shape gets its geometry type stamped on it as well. And then you get to read a double for the X and a double for the Y. Okay. Polylines and polygons are different, right? In that you still have shape type, just like here, starts the same, but then it has a box, a minimum bounding rectangle in that. Now the minimum bounding rectangle for the entire data set in the header and the minimum bounding rectangle for the shape at this level are very important because you can quickly assess, hey, do I need to draw this feature on the screen? Is it inside or does it intersect with my map area? And if it does, well then, hey, I need to draw it. And if it doesn't, then I can just not bother. So it's it's optimized that way and that. And then you need to know, well, how many lines does my polyline have? That's number of parts. Or how many rings does my polygon have? Number of parts. And then number of points. And then a parts array and then a points array. And you have to work with the parts array to know how to, like if you have a three ring polygon, 1 exterior, 2 interior, you got to know where the start and stop are on those particular rings to extract the right coordinates to build your rings in that. And so, and you might notice by this time, look, the byte order has switched to little, okay? In that. So there was some big in the header, then it flipped a little. And there's some big in the record header again, and then it flipped a little, and that. So it's a blended file uh, byte order in that, but it is specified that, hey, to be a proper shapefile, it has to be in this order at this level. Now, spin, right? So lots of, when I went through school, there was no debate, right hand rule, right? And that sort of thing. And that was always, I guess, clockwise in that. But I guess there was some controversy in that. And so uh, formats usually have to say which way they spin, okay, in that. Uh, and so holes and polygons go counterclockwise, which means that uh, exterior rings are clockwise, right? Now, this bounces between different formats. I think Oracle spins the other way. Vector tiles for Mapbox spin this way that we see on the screen. Shapefiles spin this way in that. And I think what PostGIS did, instead of going right-hand rule, left-hand rule, because people still argue over what that meant, is they have functions in the database to say, do you want the spin to be clockwise or counterclockwise? You decide, and they'll flip it for you in that. So does spin matter? Well, yeah, it does, right? Mapbox vector tiles in that. Let's actually pop out here for fun and that. So we'll take a look and we'll keep going down. And I just want to get the part to the spin, right? So this is a big, I don't remember being this big, but that's how they want their ring spinning in that. And then if they're both spinning in the same direction like this, that should mean you have like two polygons on top of each other. No, we do in that. And if they spin in opposite directions, right, then it knows to punch a hole out in that. So spin is important for GIS because is that two polygons stacked on top of each other, or do we take the smaller polygon and punch it out of the bigger one? Okay. And so what did you mean, right? So this is where spin actually becomes very important in that. So we'll go back in here. And there we go. All right, so the spin or the winding order. Right, so OGC simple features, it might actually spin the other way, and that's and that. I'm just more familiar with shapefile, ArcSDE, and Mapbox vector tiles. I know Oracle Spatial spins the other way, and that, okay, in that. But if you want to get into details, what you'll start to notice is that some do for the exterior ring, right? Some do a clockwise, but then some do it counterclockwise, which means the interior rings have to spin the other way if they're meant to be punch out or holes in that. Okay. Yeah, click here, then choose. So they have basically, don't worry internally, but if you need it spun a certain way, right? Right-hand rule is the one I learned, but there is controversy about it. So if you need them spun clockwise, they have, which everyone agrees on what clockwise and counterclockwise is in that. So if you do need the rings spun a certain way for a polygon, and you're like, oh, they're going the wrong way, well, they have functions in the database that will spin them the way you need them. You just need to say, well, what way do you want them? So what we'll do here is talk a little bit about well-known binary. So WKB, right? So it is from the OGC OpenGIS Consortium. It is used in quite a few areas actually now, and you see it showing up in more and more places. So they have many, and I mean many geometry types. We'll take a look at point and polygon and that. So they have even more codes than the shapefile, but their numbers are different. Okay, so they use different numbers in that. So it's important to have that your tools or tooling understand shapefile, understand well-known binary, understand that they use different codes for the geometry types in that. All types start off with a high or low. Okay, so in the shapefile, they don't explicitly burn a value into the shapefile on disk. What they say is read the spec, and the spec will tell you whether it's high or low in that. In well-known binary, because you could be coming from a RISC system or a, I guess, or a complex instruction set RISC or reduced instruction set RISC. So high or low, they're not sure what system made the geometry. But for them, the whole geometry is stored in one order. We saw with the shapefile that there's a mix of high, low, little, big, and it's mentioned in the spec. Here, the whole geometry would either be low or high, but because there's lots of different systems, lots of different chips, you're going to have to ask every shape, hey, are you high or low? And they reserve the first byte. It'll have a 0 or a 1 in there. 0 high, 1 low, and that. And you can look at that byte, and that'll tell you if you need to flip the numbers or leave them as is, depending what system you're on. I mean, if you're on a high system reading high, you'll be fine. If you're on a low system reading low, you'll be fine. But if you're on a high system, but the data is coming from a low system, then you're going to have to flip the same if it's crossed over for low and high in that. The next 4 bytes will be the geometry type in that. And again, that's just telling you point, line, polygon, multi-point kind of concepts, but it'll be using OGC codes and their conceptual geometry types. Okay, so is it a point, a line string? Notice how it's not polyline like that. Polygon, triangle, multi-point. They have lots of, I mean, lots of codes for different types of geometry in that. And it's different codes, right? I think polygon is 5 on the shapefile in that. But, you know, there is that little well-known byte order. The very first byte tells you whether it's 0 or 1. Whether you're big endian, little endian, high, low kind of concept. And that's burnt in at the very beginning of every chunk of geometry. So the well-known point, again, the very first byte, high or low, and then, hey, what are you, right? Almost like a shapefile in that, hey, I'm a point. And then what should follow after that are 2 doubles, okay? And that point should be A, X, and Y, and that sort of thing. Now, I don't want to get ahead of myself. There is extended well-known binary to get us to 3 and 4 dimensions, but the original spec was just basic, hey, could we just settle on how we want to do 2D geometry? We'll worry about 3 and that later. And so are you high or low? What kind of shape are you? Okay, based on that, what comes next? Well, if it says point, then 2 more doubles are coming to represent the X and Y in that order, okay? If you're polygon, hey, are you high or low? Hey, what kind of shape are you? Hey, I'm a polygon. How many rings do you have? Right? And that sort of thing. So it could be, well, we have 2 rings. We have an exterior ring, we have an interior ring, and that's the hole we're going to punch out. And then there's an array of rings in that. And so what's a ring? Right? Right? Well, the very first thing inside a linear ring is, well, how many vertices do you have? And then an array of vertices, and those vertices would be XY pairs in that. So there is extended well-known binary. Okay, so a couple things happen with well-known binary. It happens to almost every shape geometry format. Is that, hey, what about 3D, 4D, and hey, what about an SRID, like a system reference ID? We have this data set. It has coordinates. We have no idea if it's UTM, Web Mercator, and lat long. We can go look at the numbers and guess, but maybe it's Melt Bell Bears. I don't know, and that sort of thing. So yes, the OGC forgot some things. It's just sort of shapefiles. Everyone does in that. 3D, 3D, Z, and measures, and an SRID. So a shapefile does actually have specifications for 3D, Z, and measures, but hey, SRID is missing. So the original shapefile just has a SHP, SHX, and a .dbf file. The .prj file came much later. Like, whoops, we need very important information is the SRID, right? and that. So there's a recent doc if you want to get into the details in that. And so the thing is that well-known, when we get into the geometry type, it's stored as an integer. And that's a 32-bit int. And maybe there's, let's say, 20 to 30 different geometry types. An int can store, if it's an unsigned int, right? And that's what that U means, unsigned int. 0 to 428, 4.28 billion. Okay, so there's a possible 4 billion geometry types. In some systems, if it's signed, which means it can be negative, it's like it's a yeah 2.14 or something, 2.14 minus to 2.14 positive. Here we start at 0, shift everything up, so it's 0 to 4 billion. But hey, some people only have like 12 geometry types. Maybe we can push it to 20. Maybe if we, try to get creative on a weekend, we can get to 30. We could technically store 4 billion in there. It's hard for me to come up with that many kinds of geometry in that. But we can start throwing true curves and different types of curves in there and that sort of thing, tins and triangles in that. Maybe hexagons, hexagonal bending kind of stuff to get to even more complex geometry in that. But we still wouldn't get to 4 billion. So the thing here is that there's a heck of a lot of space in this unsigned integer to do some fancy stuff. And this is how they extended well-known binary in that. And so what they do is they just move up the range and start burning in the exact same geometry types, but do it for Z. The exact same geometry types, but do it for ZM in that. And so these are the codes if you want to do Zs. And what it is, they're just repeating all of the other geometry types further up in the range with a big gap between them, so that they're not even close. Right? We could put like a million point gap in between them if we want to, and we got 4 billion, got lots of space. And just repeat the sequence for, hey, all those geometry types below, but for 3D. All those geometry types below, but for 3D with measures in that. And so you just use the same sequence of codes further up in the range. And again, we're only using like about 20 to 30, and we can actually technically have 4 billion. There's lots of room, right, to hack, right, to hack this information in, which is what they did, and that sort of thing. And so a well-known binary point, we got byte order, that's good. And then so here, we, instead of getting a number in, like, say, the 1 to 30 range, we get a different number. And so there's a coding table to say, hey, are you a well-known binary point? Maybe you're a well-known binary with a Z, with measures, and maybe, oh, you have an SRID. So that number triggers us to say, oh, there's possibly an SRID in here. And so maybe my data doesn't start right away. And, right? And so if you did get a code in here that there was an SRID, then there's a heads up that, hey, the X and Y's aren't starting yet. There's going to be another int 32, unsigned int 32 in front of your X and Y coordinates that represents the system reference ID or the projection information. Then the point will start the X and Y. So we read the byte order, we get the geometry type that gives us a signal that, hey, do my X and Y start right away, or is there going to be an SRID in front of it? And if I get the signal based on the number that, hey, there's an SRID, then I know, okay, don't read the doubles yet. Read it out of the file. That'll tell me the projection information. And then I can start reading the X and Y like I did before in that. And there could be, depending what codes you get, hey, besides an SRID, read the X and Y like usual, but there's also going to be a Z there and maybe an M, right? Depending on the code you get on the geometry type. And so that'll give you enough information to know, hey, before I attempt to read the XYs, possibly ZMs? Do I read out an int to get the SRID or not? And that's how they were able to hack the format. And it's because hey, you're only using about 20 to 30 values, but you can actually store 4 billion and change in there in that. So there's a lot of room to do this kind of a hack. Right? So you get an extra int if this number comes back telling you so, and then some extra doubles in that. And again, when you're reading binary data, it's all about staying in sync with the file. And so just sometimes there's like lots of this embedded information to say, oh, by the way, there's some extra double you got to read in. Oh, by the way, before you start the coordinates, you got to read an int out to get the SRID. And this would be on every, this is burned in at the geometry level. So every point would have this, its SRID burnt in and that. So we can talk about geopackages, right? What are they, right? And so the what are they is an SQL-like container. I think I'll get into this, but it's an SQL-like container, which means it's an SQL-like database, but they specify how to store the geometry in a blob field in that. So you'll have like stock SQL-like 3 tables with columns. All they really say is that, okay, by the way, when you encounter one of these geography columns, this is how the geometry is packed or stored in the file in that. And so there will be about from 0 to 39, the first 40 bytes of the file, and that is like a header, and you hit your well-known binary in that. So the first 40 bytes tells you, I guess, but we'll get into it, but it's header information about, hey, what am I looking at? Hey, you're looking at a 3D point with an SRID. And then OGC well-known binary follows that. So they put a little bit of header information ahead of the well-known binary. And then the idea is that if you already have tools that know how to read well-known binary, then hey, once you consume this first 40 bytes, it's stock standard OGC well-known binary after that. And those are also variable length records like the shapefile, because how many vertices are you going to have in a line? Don't know. How many are you going to have in a polygon? Don't know. So you need to have a variable length record to store that shape. But those first 40 bytes, so you go get a table, find a row, slide over to the geometry column, pull out that blob value. First 40 bytes are header. Everything after that is the actual spatial data and that sort of thing. Right? And so lots of the spec here, but just in front of the well-known binary is the standard geopackage binary, right? So there's a little bit of a header, I guess. I guess I should say the standard geopackage binary starts with a header and then stock standard OGC well-known binary to pack the information in. And it's a standard, right? Well, just follow the standard and the tools will be happy in that. So the header is going to tell you, hey, are you 2D, 3D, 4D measures, and that? What's your SRID, if you have one, and you probably should, in that. And so the header is the big thing. Hey, right in the header is a magic number. So that's at 0 to 39 are the first 40 bytes. Hey, there's a magic number that says, guess what? I'm a geopackage a geopackage spatial geometry, right, in binary format. So the little magic number in there, it says what it is. It'll tell you like the version of the format. And so there'll be a specification online that you can match it against. Then there's some byte flags. So there's one byte that has 8 bits, and they use each of those. Actually, they don't. They use some of those bits to warn you, hey, 2D, 3D, 4D, hey, SRID, no SRID, kind of concept. In that. And so you read those flags to see if this next thing is coming, but you should have an int 32. I think so because this isn't unsigned in that you're probably only using the positive range, but it's usually enough. That would still get you not 4 billion, but 2 billion different projections in that. And then an envelope. So an array of doubles. So depending on whether if you're 2D, it'll be 4. If you're 3D, it'll be 6. And that. And again, what comes after that header is after that well-known binary. So those flag values, it's 1 byte, 8 bits, so just ones and zeros. So they don't even use them all. So right. So you saw this in the shapefile where there's a section where it's not being used, it's reserved for future use, right? Uh, so in the bit is it standard or extended? Is it null geometry? And then this would be in bit 3, in that or bytes, bits 3 through 1 tell you whether you're uh, no 2D, 3D, 4D, right? And that. And then in bit 0, just bit 2, like one single bit of a byte. Byte has 8 bits, whether you're big or little. And that. Now there's other formats out there. There's the .geodatabase. And so you're going to run into this if you're dealing with ArcGIS and mobile systems. And that. So the .geo database, yes, there is some drama around this format, especially in my life, right? So there is this thing called the .geo database. We've seen the file geodatabase, its directory with a .gdb in the title. This is a single file system. It's also based on SQLite 3, just like geo packages are in that. So I've worked with these .geodatabase files early, all the way back since version 100 of the runtime. And basically, at that time, they just called it a runtime file geodatabase, right? And they changed the name later in that. Actually, we'll go back here and I'll click here. So at the time in ArcMap, you needed these runtime tools to be enabled to get these features. Then there was an announcement that the runtime tools are not being ported to Pro. However, right, at Pro 2.7, you could right-click and go new mobile geodatabase. So it's weird because these databases that were in ArcMap that were not going to be ported, how magically showed up in 2.7 in that. So they were back in that sort of thing, like John Wick. I'm thinking I'm back, kind of stuff. And so they actually came back in vogue, but there's like this big announcement that they now support them. But I'm like, no, these are the same things that were back in 100, because the code I had written there still works with these, and they still works today with them as well in that. So I'm not sure what happened, right? Like I said, love to have been a fly on the wall in some of these meetings, but basically it is the same geodatabase. And you can, in Pro, the next time, if you're using Pro, the next time you go new database, look at the menu choices. You'll actually see them in that. And then all of a sudden they said, hey, we now fully support it in 100.12. But it made it sound like the database you made in Pro was different than somehow the database we made back in 100. But it's the same thing, same schema, that's for sure. Maybe they packed the internal geometry different, but the databases I made way back then, I can still open up on a mobile device today in that. There's also something called a mobile map package, but it's a much bigger thing in that. And so whereas these runtime file geodatabases, or these new .geodatabase, that's a big extension name too, they just store data. The mobile map package can store many maps with its styling. So it solves many maps versus one. It also solves symbology in that. And so today in Pro, if you're going to have a whole bunch of maps made in Pro and you got them all arranged and styled with unique value renderers, instead of just exporting out the data for each map as a runtime geodatabase. You can export the whole thing out as a mobile map package, but those mobile map packages are just zip files. If you go in there, what you find is a bunch of these .geodatabase databases in SQLite format, and a little bit of JSON that describes the layers and how to render them in that. But the mobile map package is a bigger thing. Instead of being a one thing, it's a many thing. So it's many, instead of being here's some data, it's like here's the data for all these maps, and here's how all these maps are, I guess, configured and their symbology. But yes, the data still uses the runtime geodatabase format. You can, like I said, use 7-zip, unzip the mobile map package, drop down to directories, and you'll be able to find them. Right? And so there was this thing where, it's meme time in the course, where ESRI, where they were trending towards geo packages, and the runtime had, hey, OGC geo packages were a thing, and they had samples to show you how you could work with them. Pretty quickly, 112 version of the runtime, boom, the .geo database is back, and that sort of thing. And the tooling in Pro is there to export your data out quickly. In that. So I did take a screenshot in Pro just so you know the next time you're on your database folder and you go add a database, if you go down, we're usually used to this one here, new file geodatabase. But in the list, new mobile geodatabase, and this is the .geodatabase that I'm talking about right now. SQLite container using the, I guess, the ArcSDE personal geodatabase, file geodatabase schema. So like how they store their domains, their default value split merge policies, how they store their feature classes, and that sort of thing. And so it uses that same schema, so it works quite well. And a lot of their tooling understands the geodatabase schema. Hey, we know what domains are, we know what subtypes are, we know what split merge policies are, and that sort of thing. And attribute rules and all these other things that can be stored inside them. If you want to, you can pause this video lecture and watch this video that introduces the mobile geodatabase. It's a little old, but like I said, it's been in Pro for a while now, and that. But there was this time where, hey, we had this thing over an ARC map. Is it coming over or not? Someone said no, and then it felt like got a little bit of pressure, caved, right? Hey, they're back, and that sort of thing, and that. And so you can watch this video. It's not too long, and that. So SD geometry. So who's SD geometry, which is a good question. So SD geometry is more of a ISO standard in that, and so we kind of have to be clear on which one, who's we're talking about. And so ESRI, ArcGIS, SD geometry. And so we can, within Postgres, without the PostGIS extension, because PostGIS would be Postgres's native spatial type, we can actually store in a byte A field, Postgres's blob field, geometry. And it would be geometry that ESRI put in there. But then how do you read and write it at the SQL level? You need a little bit of help. So they have a type specified where you can get the size, like how big is this binary chunk, what's the SRID, what's the number of points, type of entity, SQL type, bounding box information, area and length if it's appropriate, and then you get to the shape. It's almost like a little bit of a header information like we saw with the geo packages, and then you get to the well-known binary in that. Except, what is their binary? Their binary more than likely is, they say ESRI compressed shape, but I really believe it's SDE compressed binary. Just from growing up around these databases, that's basically what's inside them. So this format they use actually doesn't store the coordinates as doubles. It actually stores it as whole numbers, but that way they're able to pack it differently and save space. So on larger data sets, you start to see some gains. But the OGC standard is that well-known binary. It has to be a double, which is a well-known computer type in that. And so those can actually be take a little bit more space to store the same information in that. And this gets into these geodatabases that we talked about on a few slides back uh, in that. And so it is SQLite, and the data is packed in there a little bit. And then you can load SD geometry into the mobile geodatabase to query it in that. And so there are these features that let you get at the data in that. So I'm just going to go full screen here quick in that. And so you can also store Oracle. Oracle has its own spatial type called SDO and SDO topo and others, but you can choose to store the geometry in this format as well in that. It's very similar structure. Just once you get to shape, it's called points on the Oracle side. Pretty sure it's going to be SD compressed binary in the end. It's called Easterite compressed binary, but back in the day, we knew it as SDE. Okay, and so as you saw on that slide that popped is that the mobile.geodatabase, right, has geometry in it as well. How is it technically stored? So it's stored in this type of structure, and you can sort of drop a DLL into a tool that knows how to read and query SQL databases, and you can actually get work with the data with an SQL prompt, like select geom from database and that. So what about Pro? You can look at some of the details here, but in Pro you can make a new mobile geodatabase. You can put data in there, and then you can integrate this SD geometry shared object or DLL, and you can enable those tools to query the database using SQL statements. There's a list of functions. Would it hurt? Wouldn't hurt to take a look. It's a PDF, but there's quite a few. And a lot of these functions have already been specified by ISO groups, international standards agencies, and that. And so things like, creating a convex hull, doing intersections and unions, calculating area. This SD as binary says, hey, you're free to store the data in whatever format you want, but when you run this function, it brings back OGC well-known binary, right? So that way your binary format name may not be standard, but because of this function, and you can flip it into OGC well-known binary, then you can have like a standards compliant database that, hey, our database can produce well-known binary if we have to. As text would be well-known text. Lots of different things for calculating centroids and doing predicate tests like contains and crosses in that, and whether they're disjoint in that. Quite a few when you go through here, functions come along with this. Okay, calculating mins and maxes in that, and inspecting geometry in rings. So quite a few things, as you can see, quite a few functions in that. And again, this ST underscore naming convention is an ISO standard in that. So we'll get back to the lecture here. And yes, and so there is a function reference. There are instructions how to enable it. I'm going to do a demo shortly that you can watch where we bring it into the DB browser for SQLite and run a simple query once we get it all set up. It does take some configuration, right? There's this DLL from USRI you have to get. You got to drop it in the right place. Got to run an SQL statement to get the dynamic extension loaded into SQLite 3, and then you can start using the SQL statements in that. And so what is this binary specification? I think a possible answer here is, like I said, even though like some people call it USRI binary, I think it harkens back to the day of ArcSD compressed binary in that. And so there's physical and logical representations, and you can get the gory details in here, binary layout and that sort of thing in that. So this format's been around for a while in that, but it is, it does seem to be based on this. But again, the idea is to have this level in between the actual way it's stored and getting to a standards way of getting like OGC well-known binary out of the system and that. And so there's this meme time again, right? So well-known binaries around, but Easter has already had this legacy format, and using SD geometry, they can basically expose it as a well-known binary if they need to in that. And so by default, because a lot of their tooling already understand this format, and they did it with the personal geodatabase, probably doing it with the file geodatabase, then making these mobile geodatabases, if they just keep the same format and not reinventing things, it's just, find the blob field and stuff the geometry in it. Yeah. What you can do now is pause this video lecture and watch my other demo where I use a database where I created in Pro. I copied a bunch of data out of a file geodatabase into it, and then we just come with a third-party tool without Pro, and it's a tool that knows how to work with and query SQL-like containers. And all you do is dynamically load the extension, and if everything works out, you can start doing spatial queries. What we'll do now is talk about OGC well-known text. So we can do a little overview, but in the demo, you would have saw OGC well-known text come back, right? We took the parcels, we flipped them to centroids, and we convert those centroids to points in that. And so well-known text, well-known binary, these are standard formats spec'd out by the OGC in that. And so there is this keyword, hey, what are you, right? Point, line string, polygon, multi-point, multi-polygon, right? Multi-line string, and that. So there's a keyword, and then usually the coordinates that represent that geometry are wrapped in parentheses, okay? So if you're from the JavaScript world, JSON, you go, this is for functions. We never really see this in the JSON world, so it's different, right? And that. And if it's something like a polygon that has an exterior rings, you'll see a whole bunch of parentheses. You might even see like 3 parentheses start off your type and that sort of thing. XYZ values, that's if the Z values are there, are separated by a space, not a comma in that. So a single space, right? Commas are used, but they separate vertices in that. So XYZ values separated by a space. If you have a point that's represented by, let's say, 3 vertices, then you'll have like at least 2 commas in there separating the actual vertices in that. So generic patterns is keyword parentheses, and it depends what you have in there, whether you'll have commas or not. If we were doing points, we won't. So we'll just take a look at some examples in that. So if we want to describe a point, as simple as point, right, parentheses, X value, space, Y value. And it's typically, X, Y, Z order. So some stuff is, with these formats, it's always this, what's explicitly stated and kind of what's implied. And sometimes, and it's implied's okay, is if the spec or standard says, oh, by the way, this is the assumed order, then it's written in the standard that, hey, it goes X, Y, Z if Z is there. Okay, a line string. And again, this would, in the Easter world, from the shape file days and up, they call that a polyline instead. And then there's a polygon. There's the 2 parentheses. So that this would, the first one is the whole polygon. The first set of parentheses after that is meant to be the exterior ring. And there's explicit closure, not implied. So that means where you start 3010 is where you end 3010. Now some other formats, closure is implied, that it's implied that you're going to wrap back to that beginning point in that. So it depends on the format. Here's a multi-point. So here we have the double parentheses, and then each point's enclosed in parentheses, but separated because they're each individual points in that. Multi-line string. right? There's two line segments. They can be disjoint. I do have a multi-polygon in here. Here, this is where I say you can sometimes get triple, right? So this would mean exterior ring, and this would mean interior ring. It's possible that you might have multiple exterior rings, like the state of Hawaii has multiple rings representing islands and that. And then you might have punch outs on the islands that, hey, this is a lake or something. There's also something called extended well-known text. So just like they had to extend well-known binary, hey, to get the SRID in here, guess what they did with well-known text? They extended it to get the SRID, right? Simple, elegant hack, right? So why do spatial orgs always forget the SRID? I'm really not sure in that. But once it got into standard, they couldn't get rid of it in that. And so it's always an extension or an add-on to get the SRID back on. Yeah, that's the one thing about standards agency. Once it gets in the standard, good or bad. So sometimes you can get some bad in there. And yes, why? That's me complaining and whining there. So all they did was add an SRID to the well-known text. They just had to figure out a way to do it in that. And so what they do is they use the keyword SRID, they use the equal sign, and then a number, and then a semicolon. And they can use equal and semicolon because those are not characters already used in well-known text. The comma is already being used, the space is already being used, the parentheses are already being used, so they use something else in that. So, and they put it on at the front, so it's an easy thing to strip off if you do any coding like in Python. You can just split on the semicolon. Everything before the semicolon is SRID. Everything after the semicolon is OG, original, OGC, well-known text in that. Right. So it's safe to use those characters because they're not already being used. So you'll see this little text-wise, SRID is equal to and a number, and then a semicolon, and then everything after that is just regular OG, well-known text from the OGC. Yes, I agree. It's very elegant hack, easy. We'll switch gears here, talk about GeoJSON in that, which has also become a standard. So there are some GeoJSON rules that came about in that. Because we're in JSON land, right? We had kind of had to follow JSON rules, right? Braces for object things, colon for key value pairs, brackets for arrays. But is this GeoJSON rules or are these JSON rules? A lot of these are JSON rules because that's the land that this lives in, right? Comma to separate anything in an array, which is different, which also means that the one thing this shows up is that not only do commas separate vertices, commas also separate XYZ values, right? Which is a slight deviation from well-known text, but they have to because, hey, we're in JSON land and that's how arrays are done, right? So we do it for XYZ values and vertices and rings in that. So a comma to separate anything in a list or an array in that. So there are these object things, something called a feature collection. This is almost like the analogous thing on the easter side would be like maybe feature set. They're at the same level. And then inside a feature collection, it has a bunch of features. And a feature is also an object, and it can have some geometry in that. And we'll get into it. It has geometry and properties. It's a feature set has features as well, but it's geometry and something else. It doesn't use the word properties, but it uses another word that's very similar. We're going to cover it, so I don't want to have any spoilers right here. There are things in an array. So a feature collection has a property because it's an object called features, and that features is a simple array of features. And when you're in geometry, then you have a bunch of arrays depending, like a bunch of arrays for coordinates. Something like a polygon that has exterior rings and interior rings, there's a lot of arrays, right? Because there's a mini array for XYZ values, which then get organized into rings, which then get organized into polygons. So you have arrays within arrays within arrays within arrays. You probably get one more level of arrays compared to well-known text because of that X, Y, Z values being also in its own array separated by commas. Things that are implied, right? The first ring, right, is the exterior ring, right? So on rings, the first one is the exterior. Any rings after that is an interior, right? You can go to the generic layout is of the GeoJSON format is that you have a GeoJSON object, so parentheses. What's usually stated at that type level is that, hey, I'm a feature collection. And then there's an array of features and then a feature has a type, hey, I'm a feature, brace, right? I have an ID typically. I have a property called geometry and that. I have a property called properties of key value pairs, which would be, again, an object with key value pairs. And then the geometry has a type. Hey, are you point, line, point, line, string, polygon? And then you have your coordinates, which is a bunch of arrays and arrays of arrays, depending what you have in that. And the good question, SRID. The current spec assumes everything to be 4326. However, right, in the beginning, they didn't actually lock it down that it had to be 4326. So there are lots of tools, even in Pro and QJS, that if you don't tell it to be 4326, you could get JSON, GeoJSON out in melt-bell-bearer coordinates, Web Mercator coordinates, UTM Zone 10 coordinates. But for it to work with the mapping libraries like Leaflet and OpenLayers, we kind of got to, check the box that says, hey, reproject all that stuff on the way out to 4326 lat longs in long lat order. And so that's what I meant, lat longs in long lat order in that. So maybe over time they'll go back, but I'm pretty sure that the current spec is like, no, 4326 in that. And so this is, if we had some GeoJSON in VS Code, we would see, hey, type feature collection, and then features, pretty simple, right? A feature set has a lot more information on it. I think in the future, if I had one request for GeoJSON, there would be, some way of designating the data types for the properties. Okay, so these properties are key value pairs, but usually are all strings, but really some of those are numbers. And so it would be nice in the future, don't know, not anyone, they don't listen to me. It would be nice to have a way to specify what are the actual types of those properties. Is the property a date? Is the property a string? Is the property a whole number? Is the property a decimal number? That would be great. At least, those are the four. That's where you want to start. You always want a little bit more, but you want to start with those four in that. Now, if we take a look at features, and this is just looking at one, right? This would be an array of features. It'd be an array of objects. And so the object says, hey, I'm a feature. Hey, my ID is this. I have a geometry and I have properties in that, in there. And so you can go to the GeoJSON site, and they have some live demos there to take a look. Switch gears here and we'll talk about ESRI JSON, aka the feature set that I talk a lot about in certain diagrams. And this is this concept of a feature set, which is the base of the feature layer. And that feature layers usually have it's a feature set with symbology and that sort of thing, and a few other things. But at its heart of every feature layer, hosted feature layer in ArcGIS Online, is this thing called the feature set. in that. And it is specified in JSON. It does have a bit more information in it in that. And so we'll take a look at it. And so what are the rules? It's going to be the same rules as GeoJSON because, hey, we're in JSON land. Braces for objects, colon for key value pairs, brackets for arrays, commas to separate anything in an array, and that. And so then after that, it depends, well, how do they structure it? Do they consider this, when they were designing their spec, did they feel like it should be an object with properties? Did they feel like it should be an array? And so you just have to get in there and see what they did, right? Yes, and comma separates anything in a list or an array. And so you can go to the REST API, and they'll have the gory details, right? But there is this thing that when you look at a feature set, or if you use the tools in Pro, you can take any feature class that you have in a file geodatabase and save it out as useRide JSON. In that, if you don't check any boxes, it'll be useRide JSON. There is a box to say, hey, GeoJSON, and there is a box that says, hey, reproject 4326 as well. So there's usually some field aliases at the top, not always filled in. They state the geometry type high, right? In the GeoJSON, the geometry type was all the way down at each feature level, layer, or down at each feature, it states its geometry. It allows for the concept of a mixed bag of geometry, where you could have a mixture of polygons, lines, and points. But a lot of GIS systems are like, no. We want to give the whole layer the same type of symbology, like point symbology, line symbology. So it's like a cartographic issue in that. There's a place for a spatial reference, whereas GeoJSON, although you could in the past put whatever one you want on it for standards purposes, to make things easy on your phone and on your browsers, 4326, and on the mapping libraries like Leaflet and OpenLayers and LibreMap. But they also have something called fields. And fields is, I grew up in this area. This actually helps out. This is where you can say, hey, this is a date field. Hey, this is a number field. That helps out the charts. That helps out a lot of the, instant apps and that, or even Field Maps Designer that, oh, this is a date field. I need to pop the calendar widget for the user to fill in the date and that. So to have that kind of nice functionality that, hey, if I have an official date field, I'll get an official proper calendar or time widget for the user to fill in instead of them just trying to hand bomb the date. And are they doing the month first, month second, month third, and that kind of chaos in that. And then they get into features, which is an array of feature. And a feature has attributes versus properties, right? And that still a key value pair. But when you're coding it in JavaScript, it matters because you're going to go feature.attributes versus feature.properties and that. And then it has geometry in that. And so, if we look at this, this display field name for the longest time, like it's always been blank for me. Maybe that could be like the layer name conceptually. Don't know. To play around and see. But you'll see your at this level when you first come into the top object. So this brace here, I'll put my laser pointer on so that we can see. So this brace here, that implies this whole thing is the feature set. One level deep, there's a dot display name, a dot field aliases, a dot geometry type, a dot spatial reference, dot fields, dot features in that. So when I get a feature set, if I hit the dot, hey, my feature set dot, I'll get a list of these things dropping down in that. And then usually if you go to features, it's an array. So this would be the first object in the array, just like GeoJSON, but it's attributes dot key value pairs, or it would be feature, square bracket 0 square bracket would be the first feature, and you go dot attributes dot geometry and that. And like a feature set, is part of that feature layer, and a feature layer should be all the same geometry, right? That's how typically how layers are in most JS systems, whether you're ArcView, ArcMap Pro, QGIS, right? When you bring in a layer, it's all points, it's all lines, it's all polygons, so you can set the symbology for the whole layer. It can be different polygon symbology, but like a unique value render, but it's all polygon symbology with an outer stroke and a fill color and that sort of thing. Switch gears here and we'll talk about magic numbers. We've seen examples of magic numbers uh, through various slides in that. So we saw that the shapefile has a magic number and that the OGC GeoPackage header has a magic number in it as well. So this concept of a magic number that early in a record's header is where you state, hey, I'm a shapefile, right? Or, hey, I'm a OGC GeoPackage binary blob in that. So pure magic indeed. So BM, Windows bitmap, that thing, FFFE. This would be usually with text files, we just say, hey, it's a text file. But once we went to Unicode, where instead of 8 bits per character, we went to 16 2-byte data type. Well, did you go 1 2 or 2 1, right? So then we have multi-byte data type. We got a bomb issue byte order marker in that. And so one tells you whether the very first well, I shouldn't say the first 2 bytes of a Unicode text file tells you if you're high or low, depending on the code you get here. In that's a shape file, right? In that, ooh, that was the fancy one for I think OGC geometry. In that, TIFF high or low. In that, so why would TIFF be important? Hey, cloud optimized GeoTIFFs. And so even there is telling you II Intel low, M Motorola, MM RISC high, and that sort of thing. So there's a couple bytes, it could be up to 4, could be more. 4 bytes would be like a 32-bit int. And that some number that tells you what kind of file that you are dealing with. In that. A lot more here, so do check out this more magic link in that. So it's quite common. Almost every image format is going to have a little bit at the front to say, hey, I'm a JPEG. Hey, I'm a PNG. Hey, I'm an animated GIF. That sort of thing. And that. There's also EXIF metadata. We ran into this when we did our storybooks, right? In that, or story maps actually, in that. So exchangeable image file format in that. So there's usually a lot of date time information, camera settings, focal lengths, and that. There could even be a thumbnail and that, descriptions, copyright information. And what the people did is said, well, in this metadata, there's a couple ways to do it, but one way is to, hey, burn the lat long into this metadata in that. So there are 2 ways, right? You add it to the header. So in that metadata part with all the camera information, we actually burn in a lat long and that sort of thing. Or we look at another way to do it is you say, when was this picture taken? There's a timestamp. You go to the GPS log of the device and say, where were you at this time? And then you can get the coordinates that way. So that's another way to do it in that. And so EXIF tags, you can learn more about the tags here and the GPS tags there. What we want to do is actually take a look. So if you have an image and you right click on it and go properties and start to scroll down, you'll start to see camera information and that. If it's been preserved, you might get to a section called GPS and you'll see the latitude and longitude of that particular, I guess, photo in that. Now this should be -123. There might be another switch in there to tell you whether that's northern or what direction north is and that sort of thing. But yeah, so when you're on Windows, you can right click on the image, go properties, and start scrolling through to see if in the EXIF data, right, Nexus 5, that's a very old phone I had in that, but eventually you can find the latitude and longitude of that image. If you had the location manager turned on, it was active, and you allowed location permissions for the camera so that it knew it was allowed to actually burn the lat long into the photo. Switch gears and go to another format, right? And that. So protocol buffer format. And so it's a binary specification. So it's basically, it's a more generic, you have a text format, but text formats, they're bloated. they're big. You say, I want to do this exact text format, but I want to store the numbers as binary and things like that. So we can sort of like take this existing text format, maybe it's some XML, maybe it's some serialization scheme, right? And that, but the issue is that it saves stuff as text. Hey, like GeoJSON, like hey, Israel JSON, right? That's text, but they're really big, and so we can shrink them by just taking that exact format but doing it as binary in that. And so we can serialize data structures and that. There's lots of, in the early days of the web, because it's the hypertext transfer protocol, text would be key. That text is flying between the web server and the browser. But as we build bigger apps, more data, the text way of doing it gets really big. So one way to say, hey, we'll do text, but we're just going to, as we move it, we're going to flip it into binary so it's smaller, and then we'll flip it back to text on the other side. And then other people are like, why do I need to do that? Maybe I'll just shoot it right in the memory into this binary format and leave it there. And that. So it is a thing developed at Google and for encoding. It might be low or little, because as soon as you do binary, well, it's a high or low. And that's so it's supposed to be language neutral, platform neutral in that. The only way to be platform neutral would be to specify either all high, all low, maybe do a mixed thing like shapefiles in that. How is it being used? XML to binary, JSON to binary, GeoJSON to binary. So we can use this protocol buffer format to shrink the size of the GeoJSON. So the idea is that it's still going to be JSON, or it's still going to be JSON, or it's still going to be some type of XML like KML or something. It's just as we move it, we're going to like switch it to binary so it's smaller, because the choke point is the bandwidth and that, right? Mapbox vector tiles, they show you how they make them. They show you the JSON, but when it's moving from the servers to the client, it's done in protocol buffer format. So quickly take that JSON and flip it into binary so that it doesn't take up as much bandwidth. And their maps, they're faster in that. OpenStreetMap has the same option, right? So why? Text is big and bandwidth is still small. And then it would be, are we needlessly burning bandwidth when we don't need to, right? So we're burning up all this bandwidth when we don't actually need to be doing that at all. There's some other formats out there that are gaining popularity. GeoParquet in that. And this is where we're kind of, the last slide is like a precursor to new formats in that could end up as what we call cloud native format. And so Parquet is a very popular format. People looked at that and said, we could tack on a well-known binary column to that and make it GeoParquet, which is what they did, and that sort of thing. And that. So it extends or standardizes, right? Extends and standardizes because they chose well-known binary, a Parquet for spatial. So Parquet just used to be attribute data. Said, look, we can tack a column on there, make a well-known binary. We're going to make a bunch of tools happy that already know how to deal with that stuff, and then and then it can do spatial, and that's exactly what they did. Okay, and so then what is Parquet? Parquet is a column-orientated data format. So it is taking like a relational table and turning it 90 degrees. If you're constantly adding up one column, right? Why do you need to pull every row and all? Say you have a table. The table has like 40 columns. Well, if you're going to add up this one column, you have to pull all the rows, right? But when you pull all those rows, you're pulling all the other columns too. And so then that can be kind of like, inefficient. And so if your style of processing is, hey, we have to sum up this one column all the time, then flip it 90 degrees and just sum up the one column. And, and when you need to sum up the other columns, just sum up those columns and that. But if you're doing a calculation where you need all those other 40 rows, like some index calculation, then you may not be any further ahead, right? It's file based, so which means that we can have a directory of files, right? So that can kind of help with tiling, all right? Speed things up. It's binary, so it's not bloated, so that helps us with bandwidth in that. It's an alternative to CSV, which would be text, and who knows how you could chop. I mean, there's lots of ways to chop up CSV files in that. And so, but then you would have to let someone know how you did it in that. Helps with big data. And so it is the big thing about being file based and chopping up the files. So you have the concept of you have like data that covers the globe. Maybe we chop it up by some quad tree tile index, and each of those indexing tiles is a different Parquet file, which allows big data to say each server gets its own tile to chomp on and process and that sort of thing, and then we can process like the whole globe all at once in parallel. And it would depend on how many tiles you have and how many servers you have and that sort of thing. Right? It is a spatial column. It's a byte array, right? And it must be well-known text, and that's the magic. OGC well-known text, instantly standard compliant spatial data format in that. And then the question will be S or ID, because we know that well-known binary all on its own is missing something. But that's okay, right? JSON metadata. That's where you would stuff. Oh, by the way, right? This is 4326. Now, there's been some recent announcements, and I mean recent for me, like as a couple of weeks ago, maybe. So there's a new version of GeoParquet 2.0. And so from 2.0 and up, the GeoParquet is going native, which means really that the Parquet format itself is going to have a spatial column, and it's going to have choices. It can be geometry or geography. So one is like planar, flattened systems, projected systems, and one would be more like polar systems. Okay, so the Parquet format moving forward will have a geometry and a geography column, right? So before, Parquet on its own was just attributes. A bunch of open source people looked at it and said we could tack a column onto that thing, and then they added spatial to it. And I think there's been enough. I don't want to say begging and pleading, but persuasion, we'll say, to say, hey, if you ever do a new version of Parquet format, let's get this worked out in that. Now, is Parquet the best format for this? Interesting question in that. But again, right, so moving forward, you'll notice in data pipelines, if you bring a Parquet file in right away, it assumes that it doesn't have spatial unless you tell it in that. Because it assumes this Parquet file could be coming from an error where there was no spatial, so I can't assume it's there. And then you can kind of use the create geometry tool to say, oh, by the way, this column in the Parquet file actually has a OGC well-known binary in it, so it does have spatial in that, right? So it's been officially adopted in that. So whether you're using GeoParquet 2.0 or the latest and greatest Parquet format, it will have the ability to have these columns on there. And that means tools like Pro and QGIS and GDAL under the hood for QGIS and should be able to handle this. And I mean, because Post just uses GDAL under the hood, and if GDAL supports GeoParquet 2.0 or the new Parquet native format that has geometry geography, it'll be able to handle that on the driver's side as well. It does tie into something called Apache Iceberg. I've made the comment that over time, what we do for the systems is, we introduce layers. So we've gone from one-tier systems to two-tier systems, client-server, to three-tier systems typically. And so Apache Iceberg is another example of where we interject a layer. And so it would be, the concept that just above your Parquet files or just above whatever you're using, Hadoop or, whatever format you're using, there's a layer where you can specify the concept of a table. That all the files in these three directories make up this concept of a table. And what people do is they query the table with an SQL-like looking language, right? But the table's more of a virtual concept. So you, as an analyst, hey, I just write SQL against this thing called an Apache Iceberg table. And then down under the hood, part of configuring that open table format is say, oh, by the way, it's a bunch of these GeoParquet files over in this directory, and there's about 40 of them, and that sort of thing, and so it's an open table format for huge analytic data sets. Like you couldn't possibly load the whole thing into memory, so there has to be a way of doing like what we call a range query. Hey, it's just this area over here. I need you to go in and load. But then you don't have to worry about that as a person doing the analytics, right? You just write an SQL statement against this, this Apache Iceberg table concept. And in the background, the tools are hitting like Parquet or some other format. Maybe it's geoflat buffers, who knows, and that sort of thing. The idea is you don't want to know, right? You just want the query to bring back the right result. There's another concept, another file out there, flat geobuff. Rob likes, but Rob's a realist, so and that. So it's a combo of GeoBuff and, which is a protocol buffer format, right? So very complex text to binary. The text right now that it's focused on is, let's take GeoJSON, but store it as protocol buffer format in that. It's a lossless, right? So there's no loss. It's GeoJSON, but it's done as binary and compressed. Fast encoding and decoding, right? But then Flatbush, which is like RBush, R tree, and that is that you get a flat static spatial index for points and rectangles. So the idea is that you don't grab the whole file. You say, hey, I'm looking over here. You send a rectangle over, and it goes to the file and then pulls out what you need in that. So, but I am a realist. So it's a quote from a spatial data architect that worked out of Victoria that I worked with because I was working for the province region 2 in that. And so the quote, and he had many, and you end up getting many over time yourself. Data tends to stick where it lands, right? So if it lands in Oracle, it's hard to get it out. If it lands in file geodatabases, it can be hard to get it out, and that sort of thing. It's kind of there, and we can build these systems around it. And as much as Apache Iceberg solves a problem, right? It also enables the problem too. It enables this. Hey, if you have a bunch of data in Parquet format, you don't have to move it. We'll put this layer in front of it called Apache Iceberg Open Table, and people will just write SQL statements against this virtual table concept, and you can leave your data in Parquet and that. And so there's a lot of data in Parquet and shapefiles, and that. And I bring up shapefiles because if we're looking at cloud native formats and specifically cloud native spatial formats, what would work? Well, you're fighting physics here. Inertia is a tough one, right? And so for me, my experience, I've seen a few technologies. I'm like, wow, that's really good stuff, but it doesn't get adoption, right? So a great technology may never get adoption if it can't get traction, right? It needs people to start using it. It actually needs developers to start saying, hey, this stuff's really good. It's easy to work with, right? And we're saving lots of time on our workflows in that. Okay, so I've seen this happen several times. Flex Builder, its last edition, Java FX, stuff like that. It's just, great technology, way better, like Java FX, besides came with 2D drawing, came with charts, came with all this great stuff out of the box. But if you can't get traction, then it can't overtake the existing apps that have been built up in Swing and all these other products, right? So there's something real about this in that. And you are fighting physics, so an object at rest tends to stay at rest. And some of these Parquet files are big, petabytes, like collections of them. Not one file, but there can be a directory, that totals up to a petabyte of Parquet files. And the question is, do you want to spend all day moving that in some other format? Really? Is that really what you want to do with your day today? And that sort of thing. And so that is physics, that is inertia. And to move that, right, can take a lot of external force, right, in that. And then you have something like Apache Iceberg slide in to say, hey, you don't have to move it, right? Then you're okay, great, I'm not moving it then, and that it enables it to stay there. In all honesty, but in the end, as GIS people, I mean, our real focus is that it works, right? And that the query returns the correct result. That's the most important thing. Looks good, right? The apps look okay. They don't look horrible. End users aren't embarrassed to use them. in that sort of thing. And user acceptance is important. And then we can work on fast, right? And that, hey, let's just move all the data over to SSDs and watch it just rip through stuff in that. Um, instead of processing on one core, let's throw Spark at it and light up every CPU, every core we have in that. And so, there's different ways to do it, right? But again, got to work first, most important thing. But there is this issue of inertia, and it's real in large data warehouses, data lakes, and that no one wants to totally move the data, and you could potentially mess it up as you move it too. So and start breaking queries. So that's never a fun part when that starts to happen. And also another thing, and this is technology, and that given enough time, the other tech will catch up. So this happened with NoSQL databases, right? There was a flash. Hey, you got to move everything. People look. That's a lot of data. I don't want to move that. Maybe next year when we got some dead time, we'll move that. And then by next year it becomes, things are still working, right? Not broken. Don't fix it. And then all of a sudden, they'll add some features to Oracle or to Postgres, and they go, hey, you don't have to move your data, right? You can kind of keep it here. We got like, 70% of the features of a NoSQL database now, or maybe 80 or 90%. And you're like, see, I didn't have to move it, right? And there's even someone who was well versed. If I can find the video, I'll drop it in the playlist. Talking about NoSQL and big data, and his comment was, when you look at what the systems are doing, right? Most of those systems are executing what looks like an SQL statement or from a relational database. And hey, this is Apache Iceberg is doing the same thing, right? Hey, it's this open table concept that uses a language that looks just like SQL to query. And so then you're running SQL workloads in the end, because it's a nice SQL. A lot of people know it from databases. Nice language. You understand how the group buys and the order buys and the halvings are going to work, and that. And it's a great way to analyze data quickly in that. Well, the speed that's up to the system. You writing the query is the quick part in that. But that's the thing. If something stalls or something takes too long, then the Oracle, the Postgres, the Microsoft SQL servers will keep adding more features. And what you said they couldn't do 6 months ago, now they can. So what are you going to do now? Right now they can do it, and so it gets into any product like first to market and that sort of thing, and getting market share and that. But if you give the technology enough time, it's going to catch up to where you're at. And then it won't be these old relational databases. It'll be, hey, wow, look, Postgres we can query JSON. We can store JSON in the database. We can query it just like MongoDB. That's it. There's another example. There was a MongoDB. Hey, there was this phase of XML databases. Hey, if we're going to be moving XML back and forth on the web, let's just keep everything in XML. And then it was hey, if we're going to be moving GeoJSON back and forth on the web, hey, let's put everything in MongoDB. But now a lot of what MongoDB can do, well, Postgres can already do. It's been doing for years, right? And so it can claw back that market share that it lost, right? And so just a note on the demos, and this would be some of the videos that are in the playlist that talk about these cloud native formats and the future and what they think is coming. Stuff like Kepler GL and Deck GL and flat GeoBuffs, and the other one is from FME, where they go over some of the formats we just went over, Parquet and that. And so it's good to go through those demo videos from those people and see what people are trying to work out, what the problem is, what people are trying to work out in that. But we'll see what happens, right? We're fixing to find out, and so we'll see what happens in that. Like I look at the flat GeoBuffs, I'm like, yeah, that's really good. I like that in that. But right. Could it overtake Parquet? Parquet's just got serious, right? About, okay, moving forward, spatial is first-class citizen then they're going to be able to claw back some of that. And if they come up with a good indexing, spatial indexing range kind of queries, then yeah, they'll have something, and inertia will turn in their favor. Talk a little bit about cogs, right? In that, and so it's a cloud optimized GeoTIFF. Here's an interesting thing I noticed. A lot of these cloud native formats that they talk about, especially GeoTIFFs, yeah, you can't load them in a browser directly. They would need a lot of help, which I find somewhat amusing in that. So it's a cloud optimized GeoTIFFs. That usually means that they're optimized to be read, and the way they're optimized is that you only read a portion of the file, not the whole thing. So they may have an image that covers the whole globe, but you're just looking at a small part in Northwest Territories, or maybe somewhere in Ontario, or maybe you're over in Africa in the Gulf of Guinea, again, for some reason, out in the water. And so what is it, right? It is a TIFF, right? And this is used a lot in remote sensing because the format is kind of open, kind of royalty free, kind of sort of, in that. It is a GeoTIFF, so it has the spatial information embedded in the metadata. And it's tiled, right? And because it's tiled, then it's optimized for reading, where you don't have to grab the whole data set, just the portion that's in your area in that. Also, that because it's a file, then you don't need a server, right? So you don't need to spin up a VM on Amazon Web Services, have it running, install some software in there like GeoServer or ArcGIS Server to flip the GeoTIFF into a format that the browser can handle. But again, browsers aren't going to be able to load these without some help in that. And then the whole idea is because it's tiled, then you can take advantage of HTTP GET range requests. So just get me the data in between these 2 points, like Xmin, Ymin, Xmax, Ymax, and that would be the concept. But there does have to be some internal tiling scheme. So what it usually has to do is has to reorganize the TIFF and chop it up. Typically, they also want reduced resolution pyramids on these GeoTIFFs, so that if you're zoomed way out, you don't send them the really fine base data. You send them a reduced resolution pyramid to them, and so that's sometimes called overviews. In that, I might add that to the slide later, that it has overviews and it's tiled. And you can get details on cogs here. So there's COPIC. There's lots of different ways of saying this, right? Cloud optimized point cloud. So a cloud optimized point cloud, right? That's what it is. So you can get like a one big LAS file, and if your computer can go grab all 6 billion points and throw them on the screen, that's great. But otherwise we have to optimize it in that. So it is technically a LAS 1.4 file system. So it's LAS would be compressed LAS data, LiDAR data. Version 1.4, which gets into like how it's classified, it has to be tiled, right? So you can see a concept here, one big file, tiled, and that kind of stuff. It has an octree kind of indexing scheme on the tiling, and you can, because it's tiled, then you can say, hey, just get me this particular one. So you can get these HTTP GET range requests in that. And there's more details on it. So it does take some time, and this is something I noticed actually with QGIS. QGIS, every time it sees a LiDAR file or a LAS file or a LAS file, if it's not cloud optimized, the first thing it does is it completely reorganizes the data. So it's almost better to use something like Poodle, PDAL, that's what Poodle, as people call it, to actually get your LAS or your LAS files into this cloud optimized point cloud, so that the products don't actually consume like double the disk space as it reorganizes it for speed and that. And again, it's the concept is we're going to use one big file, but we're only be requesting portions of it. So if you need to re-examine a topic or need clarification on a term or concept, or just have a question, you can get an answer by posting a note on one of the discussion boards for this course. This concludes this lecture.